sac136, problem number 1. Chunk of ice at below the freezing point is put in a bucket of water, and the question is, given that the final temperature is 1.2 degrees Celsius, how much mass of water, or what's the mass of the total amount of water that's in the bucket in the end? Alright, I want to draw a quick sketch of this. Before you got a chunk of ice, I call it M1, the mass of it, M1, 0.467 kilograms. At a temperature, I'll call that T1, minus 12.5 degrees Celsius. And besides that, we got a bucket with some water in it, and M2 is what we're looking for, the mass of the water in the after picture. Well, the mass of the water in the bucket. If we got M2, we add that to M1. In the end, after we put that in there, that'll be the total mass of everything. But they don't give us the mass of the water in the bucket. So we got to find that, add that to M1, and we got the answer. We do have a temperature. I call it the temperature of water sample number 2, T sub 2, 24.0 degrees Celsius. Alright, in the after picture, somebody has put the chunk of ice in the bucket. The temperature of the ice has risen to the melting point, and then the ice has melted, and it's warmed up some more. In the meantime, the water that was originally in the bucket cooled down some, so they all come to some final temperature that I'll just call T. Which is unknown. But both samples of water do come to that same temperature, and of course we don't know what the we do know what the final temperature is. It's 1.2 degrees above 0 Celsius. Alright, I think that's enough sketch, and we're ready to get started here. Let's see, keep track of the heat that flows from one substance to the other. In fact, what I'll say is the total amount of heat into both of the samples of water is equal to 0. So a positive amount actually flows into one substance, and a negative amount flows into the other substance, which means heat actually flows out of the other, I shouldn't say substance, but the other sample of water, because they're both the same substance, they're both water. So I'll say there's the heat to warm the ice, from minus 12 degrees something, from minus 12.5 degrees Celsius, plus heat to melt ice, this is all heat into the sample, plus the heat into the sample to raise the temperature up to 1.2 degrees. Heat to warm water that was ice. So the liquid water formed when the ice melts, but just that part of that particular sample. Heat to warm water that was ice to 1.2 degrees Celsius, the final temperature of everything, plus the heat that has to flow into the bucket of water. And of course, it'll be a negative amount because heat actually flows out because this stuff cools down. So heat to cool the sample that was always water. I think I'll just call it always liquid. Liquid water to 1.2 degrees Celsius, starting at the 24 degrees, equals 0. And I do want to emphasize this last term is negative. You don't add heat to something to cool it. If you even say that you add heat to cool something, then you're going to be adding a negative amount of heat, and that's the way we're looking at it here. All right, I want to identify the temperature changes specifically. We're going to need, in order to find out how much heat you need to warm the ice from minus 12.5 degrees to 0 degrees Celsius, we need to know the temperature change. Heat to melt ice, there is no temperature change. That all occurs at the freezing point at 0 degrees Celsius. We don't need a temperature for that one. But temperature change, there is no temperature change. For this one, heat to warm the water that was ice to 1.2 degrees. That's from 0 degrees to 1.2 degrees. And there is a temperature change there, plus 1.2 degrees. And then heat to cool the always liquid water to 1.2 degrees. That's from the original temperature of 24 degrees. So let's get those temperature changes. I'll call this delta T1, and it's going to be the final temperature there, which is 0 degrees. I'll call it T1 final minus T1 initial. The 1 for sample number 1, that's the water that was originally ice. And here it is still ice. 0 degrees is its final temperature, solid water, minus 12.5 degrees Celsius. And that's a temperature change of plus 12.5 Celsius degrees. It is conventional to reverse the order of the Celsius and the degree when you're talking about a temperature change, but I'm not actually going to hold you guys responsible. If you remember to do it, please do it. You really should do it, but it's not important enough that I'm going to take points off on a test if you write Celsius degrees for a temperature change instead of, or degrees Celsius instead of what it should be, Celsius degrees. Should be Celsius degrees. Delta T1 prime is what I'll call temperature change. Well, let's title this one. So warming ice. From minus 12.5 degrees Celsius to 0 degrees Celsius. And delta T1 prime, It's going to be the temperature change that occurs when you warm water that was ice from 0 to 1.2 degrees. Was ice from 0 to 1.2 degrees Celsius, and that'll be T1 prime final. It's always what a change is, final value minus initial value, minus T1 comma initial. And of course it's T prime as well. So we've got 0 degrees, I'm sorry, 1.2 degrees. Let's go ahead and erase that. .2 degrees Celsius minus 0 degrees Celsius, or 1.2 Celsius degrees for delta T1 prime. And then the third thing, I call it cooling. Always liquid. Water from 24 degrees. So what it went from and to, let's take a look up here. Yeah, 24.0 degrees Celsius to 1.2 degrees Celsius. Because everything wound up at 1.2 degrees Celsius. So that's cool. And our delta T2, I'll call it, is going to be T2 final minus T2 initial. It's still part of the subscript, which is final is 1.2 degrees Celsius minus the initial 24.0 degrees Celsius, and that looks like about a 22.8 with a minus sign. Celsius degrees as our change, a negative 22.8 Celsius degrees for our change in temperature. So now I go back up to here. The heat to warm the ice, that's given by the specific heat. If I call the heat Q, we're talking about MC delta T. So that'll be, they call this M1 times C for ice. So we got M1 specific heat, let's call it C sub S for solid, and then delta T1. Alright, plus the heat to melt the ice at 0 degrees. There's no temperature change here. This is latent heat of fusion we got to look up. I'll call it L sub F for the latent heat of fusion. So it's just M times L. This is the mass, and this is the amount of energy per kilogram that it takes to melt it. Over here, this is the mass. The specific heat is the amount of kilogram per Celsius degree that it takes to change it, its temperature by a certain amount, and then multiply that times the number of degrees, number of Celsius degrees by which the temperature is changed, and you get the total amount of energy that is used to bring about that change. And then the third step, another MC delta T. This is the water that was ice, so it's still M1. But now it's a liquid, so we're raising the temperature of a liquid, so I'll use the specific heat for liquid water as opposed to the specific heat for solid water as was used over here when we were warming up the ice. Now we're warming up the liquid water. And then times the temperature change that the liquid water undergoes, what I call delta T1 prime, the 1.2 degrees. It went from 0 up to 1.2. And then plus, we're up to this fourth term, the heat to cool the always liquid water. So that is a liquid. That'll look just like this term, except we've got an M2. It's the other sample of water, the water that was always liquid rather than the water that was originally ice. But it is a liquid, and it experiences a temperature change of what I call delta T. And I think I want to call that delta T2. Take a look at it up here. Yeah, that's what I had originally called. I just left off the subscript 2 here. Okay, so it's delta T2, and that's all equal to 0. So just copy that last bit of that equation. Now the plan is to solve for M2, and that's the amount of liquid, the mass of the liquid that was originally in the bucket. Add that to M1, the mass of the water that was originally solid ice, and you get the total mass of the water in the bucket at the end, which answers the question. So let's go ahead and solve this for M2. I think I'll subtract all this stuff from both sides. So I got M2 Cl delta T2 is equal to M1 Cs delta T1 plus M1 LF plus M1 Cl delta T1 prime. And I think I'll factor out the M1. There's an M1 in every term on that side. So that's M1. Oh, and by the way, I subtracted that from both sides, so it's negative of that. Now I got a negative M1 times Cs delta T1 plus LF plus Cl delta T1 prime. Now I'll divide both sides by Cl delta T2, and I'm left with M2 is equal to minus M1 times Cs delta T1 plus LF plus Cl delta T1 prime, all divided by Cl delta T2. So now I got to substitute values with units. Well, let's look up some of these values. Cs, that was the specific heat of the ice. How much heat per kilogram you have to add per Celsius degree to increase the temperature of the substance. Cs, specific heat of solid ice. I looked that up in a textbook. You could also look it up on the internet. I found 2100 joules per kilogram Celsius degree to be the value given in the textbook table, in which I found it in SI units, with the energy unit being the joule. And then the specific heat for the case of liquid water, how much energy per kilogram per Celsius degree it takes to warm up the liquid water. I got, I found 4186 joules per kilogram Celsius degree as the given value. And then the latent heat of fusion, also known as latent heat of melting. The amount of heat, latent heat of melting would be the amount of heat that it takes to melt, amount of heat per kilogram it takes to melt the substance. And that was given as 333,000 joules per kilogram. Just joules per kilogram, no Celsius degree in the denominator for this one, because we're talking about latent heat of fusion or latent heat of melting as opposed to specific heat. So substituting those values as well as given quantities, let's see what we find. M2 is minus, we were told, M1 is the mass of the original amount of ice, which was 0.467 kilograms. And then delta T1 we found to be 12.5 degrees Celsius. Well, 12.5 Celsius degrees was the temperature change. And I left out the C sub S, so I think I want to actually put that in order. So I'm going to erase that, and then go back up here. I got the M1 out front. I want this big fraction. Copy down the C sub S, 2100 joules per kilogram Celsius degree. And now that temperature, temperature change, I was so anxious to put down the 12.5 Celsius degrees as delta T1. Then plus, I got LF, which is 333,000 joules per kilogram, and then plus the CL was 4186 joules per kilogram Celsius degree, times the delta T1 prime, which that was once the ice was melted at 0 degrees, the temperature change that occurred when you warmed that up to 1.2 degrees Celsius. From 0 to 1.2 was, of course, 1.2 Celsius degrees. And then down in the denominator, I got CL, which is the 4186 again. Joules per kilogram Celsius degree, and then times delta T2, which was that negative value, went from 24 down to 1.2, minus 22.8 Celsius degrees. Evaluating that, we find M2 to be 1.78 kilograms, according to my calculator, and the total mass, M, I'll call it, being the amount of ice that we started with, or the mass of the ice that we started with, plus the mass of the water in the bucket we started with, which will be the 0.467 kilograms, plus what we just found. And I find that to be 2.25 kilograms, right at the very bottom of the page, none too soon. We got our final answer for SAC 136, problem number 1.